You should keep track of how many different places I filmed videos for this class. All right, the very last part of topic 5.3 is about ozone. Ozone is O3. I'm sure you've heard of ozone in the context of the ozone layer, and it's something that protects us from the sun's UV rays. We have oxygen present in the atmosphere in two main forms, O2 and O3. If I were to draw the Lewis structures of each one of them, oxygen has an OO double bond, whereas ozone has a resonant bond between single and double. You'll learn more about what that means later, but this is the one on the left is a double bond. The one on the right isn't a double or a single, it's more like a 1.5 bond. If we look at the bond enthalpies associated with each one of them, you'll see that the double bond is stronger than the 1.5 bond. Now, because this bond is weaker, it can be broken, excuse me, it can be broken with wavelengths of light that are less energetic, that are closer to the visible spectrum, and in fact, well within the UV range. And this can break anything that's less than 300 nanometers in length, whereas O2 can break light that's less than about 200 nanometers in length, or wavelength. What that means is this can absorb a wider range of light than O2 can. And when I say absorb, when it absorbs those UV rays from the light, what it does is it breaks the O3 apart with that. I'll tell you more about that in a little bit. Perhaps you might be asked to calculate the energy needed to, or from the energy needed to break a bond, you might have to find the wavelength of light needed to do that. So in ozone, the bond enthalpy is 363 kilojoules for a mole of bonds. Meaning if I wanted to break one single bond, a bond, I would have to convert that. So this means it's 363,000 joules for an entire mole. I want to know how much energy for just one single bond. Well, how many bonds are in a mole? 6.02 times 10 to the 23rd of them. So the energy needed to break just one of these bonds, 363,000 divided by 6.02, E23, is 6.03 times 10 to the negative 19th joules to break just one bond. The way that happens is a single particle of light, a photon of light, comes in and hits this bond and is absorbed by it and has the right energy to break it. Obviously, that photon of light is coming from the sun. It's a great sun. Okay, so this is to break one bond. I want to now find the wavelength of light needed to break that bond. I included in here some formulas from your data booklet. In table 1, we see these two formulas. In table 2, we're told that the speed of light is 3 times 10 to the 8th. That's this variable. And we're told what Planck's constant is, h, 6.63 times 10 to the negative 34th. So the first formula I'm going to use is E equals h nu. E is energy, and it needs to be in joules per one photon. So I can take this value and plug it in there. H is a constant from table 2. And what this is going to give me is nu, which is the frequency of light. So I'm going to take my answer from the last part of the problem, divided by 6.63 times 10 to the negative 34th gives me the frequency, which is 9.09 times 10 to the 14th hertz. The question, however, wants me to find the wavelength. To find wavelength, I need to use the formula from up above. C equals wavelength times frequency, or it has frequency times wavelength first. C is the speed of light, which is a constant in that table. Wavelength is what I'm solving for. So I'm going to take 3 times 10 to the 8th and divide by my answer to the last part of the problem. And I get 3.3 times 10 to the negative 7th meters. converting that from meters to nanometers, although the question isn't specific about what answers it wants, I know that 1 nanometer is 1 times 10 to the negative 9th meters, which means this will come out as 330 nanometers. Anything with more energy than that will have a wavelength of less than or equal to 330 nanometers. To be honest, I haven't seen any problems like this on the IB exam, but it's definitely worthwhile to be discussing because it's kind of the why we care of chemistry. Now, if you were asked to find the wavelength of light needed to break a bond in molecular oxygen, now we're talking about O2, where we know the bond energy to be 498 kilojoules per mole. Pause the video, try going through the same series of steps and see what you come out with for the wavelength. I'm going to go ahead and solve it. 498,000 for 6.02 times 10 to the 23rd molecules. How much for just one molecule? So 498,000 divided by 6.02 E23 gives me 8.27 times 10 to the negative 19th joules. Now I can do E equals H times nu, and then I'm going to do C equals lambda nu. 8.27 times 10 to the negative 19th equals 6.63 times 10 to the negative 34th times the frequency. Giving me a frequency of 1.25 times 10 to the 15th hertz. Now plugging in over here, speed of light is still 3 times 10 to the 8th. I'm solving for wavelength. That should say 15th off to the right, it got a little cut off. So 3 times 10 to the 8th divided by 1.25 times 10 to the 15th. And I get 2.40 times 10 to the negative 7th meters, which is 240 nanometers. Anything less than or equal to that. So the moral of the story is O3 can absorb a wider range of wavelengths, making it more useful than O2 for filtering out UV light out of the atmosphere. In areas of the world where the ozone layer is thinner, meaning it's not really a full layer, but meaning there's less ozone in the atmosphere, skin cancer is much more common. I think there's a statistic, something like 1/3 of Australians get skin cancer. And that's a result of a combination of fair skin coupled with less ozone in the southern hemisphere. You may also ask for the mechanism by which the ozone breaks down and forms. So formation of ozone, O2 turns into O3. First, the O2 molecule breaks apart into 2 OOs. When you see just the O with a little dot there, what that means is an oxygen radical, meaning it has this unpaired electron on it that makes it super reactive. Then one of the OOs that forms bonds with an O2 to form an O3. If I ended up balancing this reaction, this has to happen twice for every time the other one happens. So then when I cancel things that appear on both sides of the reaction, I cancel those, and we end up with 3O2 forms 2 O3 molecules. Ozone also breaks down, and it breaks down by the reverse mechanism. This one can be catalyzed by what we call ozone depleting substances. Things like CFCs, chlorofluorocarbons, that are said to be bad for the ozone layer, are bad for the ozone layer because they help this break apart. So this is a reverse process. When this top reaction gets multiplied by 2, we end up with 2 O3s forming 3 O2s. I care with regards to ozone far more that you understand the big picture. That is that ozone can absorb a wider range of UV light than O2 can, and therefore is more useful for blocking UV. And the reason it can absorb a wider range is because it has a lower bond energy.